Hello. Yeah, so I'm Mykhailo Kuian from Case Western Reserve University. So this research was done in collaboration with Ronnie Lau from Jonas Kepler University and Lothar Reichel from Kent State University. So the motivation of this research was solving ill-posed inverse problems. So, well, ill-posed problems they often arise when one would like to solve so-called inverse problems. As you probably know, you're working with inverse problems. Really, typically they are ill-posed. And inverse problems they arise when one would like to determine the cause of an observed effect. So inverse problems are inverse of direct problems, yes. So like image restorations, remote sensing. Well, it's a really broad type of problems. Well, in this research, we explored classical Arnoldi process. So Arnoldi process used a lot for solving ill-posed problems. So it's iterative method. Yeah, so application of n steps of the Arnoldi process to a compact linear operator, it reduces the operator to n plus 1 over times m upper Hessenberg matrix. That's a Hessenberg matrix. It's a classical one followed by Arnoldi process. It gives an orthonormal basis for an m plus 1 dimensional Krylov subspace. Typically, m here is fairly small, actually much smaller than the dimension of the operator. This makes it possible to compute and approximate solution very efficiently. Well, the good side of Arnoldi is that only action of the operator A on vectors of functions is required. Yeah, we don't need to compute a joint operator, which can be a big problem. Arnoldi-based methods for ill-posed problems, they have big or broad application, yes, and they got considered they got strong attention in the literature. Okay, so what is our plan? So we in this research we describe and analyze a simple method for the solution of linear ill-posed operator equations. We will apply regularization by Tikhonov and also compare it with truncated SVD on the reduced problem. We also do some computed example, including tomography example. Okay, well, so let's consider equation number 1. AX equals Y. A here is a linear compact operator that acts on a separable Hilbert space from X to X. Well, of course, I'll define a product on the Hilbert space. Let X dagger denote a unique solution of unique solution with minimal norm of operator equation 1. So, or like we also call it least square solution. Yeah. Well, what is the problem here? Well, if you have a compact operator, so from classical spectral theorem for compact operators, well, if we know that if A is compact linear operator, the set of its eigenvalues, they accumulate to 0. Yeah, so the set of eigenvalues is countable, and it has no accumulation point different from 0. So it means all the eigenvalues, they converge to 0. So it's a big problem. It makes inverse operator to be unbounded. So if eigenvalues approach to 0, so the inverse is unbounded. And this makes the problem to be ill-posed, problem 1 to be ill-posed. So singular value of operator A, singular values of square roots of A star are A eigenvalues. So consequently, they also converge to 0. So since the singular values of operator A cluster at the origin, operator A doesn't have a bounded inverse. So the solution of the least square problems, 1, therefore, generally doesn't depend continuously on the data. The computation of the solution of equation 1, therefore, is an ill-posed problem. So because A is compact, as we figured out from classical spectral theorem, equation 1 is ill-posed problem. Okay, so what can we do in this case? Well, in many applications of operator equations, AX equals Y in science and engineering, the right-hand side, Y, it lives in the range of operator A is not yeah. So in practice, we get some noise data. Yeah, so we never have exactly correct data. So we have some perturbation, yes, Y delta, which is known, and the real solution we don't know. The real data usually we don't know. Well, we assume that at least our noise is bounded. Yeah, so the norm between the real data and perturbed data is smaller than some delta. We would like to compute an approximation solution of this problem. So what is the minimum of the norm of the difference AX minus? And that is an accurate approximation of the least square solution. Okay, so what is an idea of regularization? So regularization is an instrument that allows to solve in post problem. So we replace original operator original operator A with nearby operator A regularized. Yeah, so that also acts from Hilbert space X to X, and it has a bounded inverse. So this, instead of the original equation 1, we solved this one surrogate equation. A regularized times X equals Y per 2, Y delta. Generally, regularized operator depends on the level of noise. And we approximate the real solution, X dagger, by some approximation. Yeah, we call it X delta regularized. Okay, we also define a discrepancy principle. Yeah, so what is so if we have parameter alpha to be fixed, constant, larger than 1, the regularized approximate solution is said to satisfy the discrepancy principle if this difference, yes, the norm of this difference is smaller than alpha delta. Yes, so we call this inequality the discrepancy principle. It means that our regularized solution, yeah, should not, well, multiplied by original operator, yes, is not very far from the data. Okay, so, well, so here we can see the Arnoldi algorithm for compact operators. Well, of course, it works for, originally it was invented for matrices, yeah, but it also can be applied for general compact operators if possible. So, well, so the idea of Arnoldi algorithm is to construct Krylov subspace. Yeah, so we firstly select our original noise data, vector Y delta. Yeah, we normalize it. Yes. We construct orthogonal Krylov subspace. Yes. As a result of Arnoldi algorithm, you can see we get a decomposition. Yes, so our original operator times VM. VM is a matrix whose columns are orthogonal vectors of Krylov subspace. So this VM, it contains orthogonal vectors. M plus, well, first it has extra vector, vector from Krylov subspace, and H M plus 1, M is Hessenberg matrix. Well, so the span of these vectors, yeah, it's called Krylov subspace. So it's pretty classical instrument for solving ill-posed problems and inverse problems. So, well, the structure of Hessenberg matrix can be, we can see it here, yeah. So it looks like triangular matrix with extra diagonal under the main diagonal, yes, and well, it has this extra row, this element. So it's called upper Hessenberg matrix. Well, again, these coefficients of Hessenberg matrix, they're computed, you see. So we get from Arnoldi algorithm. So we get this orthogonal basis of the Krylov subspace and coefficients. Okay, so we have this Arnoldi decomposition. Well, how can we use it? So what is the idea of Arnoldi? First of all, so we choose how many steps of Arnoldi algorithm should we make? When should we stop? Because if our operator A is finitely dimensional, yes, infinitely dimensional operator, yes, then well, Arnoldi will never stop. Yeah, we'll get infinitely many vectors, and infinitely many coefficients. Well, so if A is just finitely dimensional operator, of course, Arnoldi algorithm is guaranteed to stop. Yes, it cannot. The number of steps cannot be larger than dimension of the operator. But what if operator A is an infinitely dimension? Okay, so the question is, what M should we choose? How many steps of Arnoldi algorithm should we make? Okay, so we choose M in Arnoldi algorithms so that the subdiagonal entry, this last element of Hessenberg matrix, see, here it is smaller than a user-specified tolerance, epsilon. Yes, the theorem 2 below shows that such M exists for any given epsilon. Yes, so no matter how small M, we always can. Okay, so first of all, from classical analysis, we know that if A is compact operator on Hilbert space, then if this is Vm, set of Vm is orthonormal sequence in Hilbert space, then for any compact operator, the limit of this product converges to 0. So AVM converges to 0, yes, for any compact operator, yes, if Vm is orthonormal sequence in Hilbert space. So based on this lemma, we can prove theorem number 2. So if we apply Arnoldi algorithm, yes, and it does not break down, so if you have infinitely dimensional operator, then limit of this element hm plus first m converges to 0. So this element converges to 0 is guaranteed by theorem number 2. Okay, so, well, assume that we apply infinitely many steps. Yes, so we have infinitely dimensional operator. We can apply in theory infinitely many steps of Arnoldi that will determine the operator, yes, of this orthonormal vectors and the infinitely large Hessenberg matrix. Yes, so then formally we can write operator A as a composition of these operators. So V, which contains orthonormal basis, Hessenberg matrix, and self-adjoint of V. Well, we know that for any epsilon, because this hm plus first m converges to 0, for any epsilon, we can find such m that hm plus first will be smaller than epsilon. And well, let's substitute this formal decomposition by this one. So now a epsilon now is finitely dimensional operator. It's an approximation of original A. Yeah, but now it is finitely dimensional. So from theorem 2, we know that the norm between finitely dimensional and infinitely dimensional operators, yes, is bounded by epsilon. It also converges to 0 with m, if m is sufficiently large. So in other words, we substitute infinitely dimensional operator by finitely dimensional operator. Well, so now let the leading m times m submatrix of Hessenberg matrix is non-singular, then the minimization problem, yes, can be simplified to this one. Yeah, it's pretty well-known fact. Yes, fact. So we instead of original problem, we can solve this one. Yeah. So now H is relatively small. Yes. It's at least finitely dimensional, or if you on practice, it is pretty small matrix. Well, so we can solve it this problem after we applied our Arnoldi process. Okay, but here another problem that this new small problem, it also can be ill-posed. Yes, so matrix HM also can be relatively ill-posed. So we also can regularize it again one more time. So we apply Arnoldi and algorithm, and then regularize it. So so we turn to how much the solution of original problem and this new one surrogate problem differ when we solve these equations by Tikhonov regularization. So by theorem number 3, if you consider Tikhonov regularization of original operator problem, yes, you see A, which might be infinitely dimensional, and our surrogate problem, yes, so with infinitely dimensional operator, then it can be shown that the difference so the solution of surrogate Tikhonov regularized problem, it converges to original. Yes, so this it's a new theorem. It's another strong fact used in this research that solution of this second equation, of surrogate equation, converges to original. Well, of course, if epsilon converges to 0. Okay, so we regularize the reduced problem. Again, remember that we have to solve this problem, yes? This is our Hessenberg matrix. You want to simply first a basis operator 1, 0, 0. So since the matrix HM typically is small, comparing to dimension of A or has moderate size, we may compute its singular value decomposition. Yeah, so we apply SVD. We find SVD of H. Well, let's say well, it has M as its dimension is M. It has M non-zero singular values. Well, like another approach to solve, well, to regularize ill-posed problem is to apply a truncated SVD. So what is idea of truncated SVD? We simply make the smallest single values, we set them to be 0. Well, so this defines the matrix, the new matrix HML. Yeah, so we just made all smallest singular values except the so L largest to be zeros. So in this case, yes, we get this new matrix HML. L is chosen as small as possible so that this norm is, well, so we satisfy the discrepancy principle. And get approximate solution. Yeah, so X delta regularized. In the Tikhonov regularization, we solve this problem. So this original surrogate problem is original to this one. And the solution can be expressed by direct formula here. Yes. I remember in Tikhonov regularization, we need to select a regularized parameter lambda. Yeah, so this lambda, it's actually the whole problem itself, how to select this lambda. Well, we select lambda here to satisfy discrepancy principle. Yeah, so based on discrepancy principle, we determined our lambda. So it's another question how to find it. Yes, so how to solve this minimization problem. But pretty typically, it's not very hard to do numerically. So and finally, we get our regularized solution. Yes. Remember our surrogate solution of original least square problem. This is it. Okay. So again, so by theorem 3, yeah, it's guaranteed to converge to original regularized problem. Okay, we also did some numerical examples. So we just tested our Arnoldi Tikhonov approach. Firstly, we tested it for like classical integral equations, like this is like Phillips equation. Yeah, it's like one of the classical benchmark because the exact solution is known. Yeah, so but we apply our method to it. So the integral equation Phillips, yes, is discretized by Nystrom method based on the composed trapezoidal rule. Oh, well, we used MATLAB here to test these computations. So what we did, we added 1% relative white noise to the data and checked how, okay, what was the restored solution. We also, you can see result here. So for Phillips equation, so the true solution blue and the computed solution. So when we applied Arnoldi Tikhonov, you see approximation is super accurate. Yeah, well, if you compute data, it was so noise level was neglected. Remember also we can solve it by truncated SVD. Yes, so if you solve it by truncated SVD, well, the accuracy is also pretty good. However, remember the problem of TSVD is, well, computing SVD is usually an expensive operation. So if we can avoid it, it's better avoid. Yes, so yeah, it's a powerful but numerically expensive operation. Well, so the accuracy of them are pretty comparable. Of our new Arnoldi Tikhonov and applying a TSVD are pretty comparable. We also checked another classical integral equation Shaw. So why it's like benchmark, because the real solution, exact solution, is known. We compared it with, well, a restored solution. You see accuracy there was also pretty high, and it was comparable to applying truncated SVD. Another another example we did, numerical example, was applying this to computational tomography problem. So, let me just give you some general information of what is going on here. So, we reconstructed an image, yes, X from the line integral data sinograms. So in tomography, what we you can imagine tomography as an array of images. Yes, so for some set of angles, usually from 0 to 180, so degrees, we compute the image. Yes, so we have like a set of some number of images. That depends on how many angles do we use. So mathematically, it can be written as this problem. Yes, so X dagger is discretized Shepp Logan phantom. This image we want to restore as A is discretized radon transform operator. Y delta is noisy projection data for many angles and detectors. So yes, we want to find approximation. Yes, so this restore this image. Well, usually in the classical way of solving this problem, and what is realized in MATLAB is so-called FBP algorithm. It's filtered back projection method. This function is realized in MATLAB, so we just compared our algorithm with what MATLAB have, with this classical FBP approach. As you can see, when we added 1% of so this problem, why it was so interesting, because tomography problem is well known to be superimposed. It's like very imposed. A problem, as you can see, it's super sensitive to noise. We added 1% of noise if image is pretty large, like 2000 by 2000 pixels, then you see this relative error is pretty large. Well, so for classical filter-backed projection, it gives us almost 50% of noise, while our Arnoldi Tikhonov approach gave only around 17. So you see, it gives like big advantage in noise. Yeah, well, so what are conclusions? Yes, so Arnoldi is pretty workable, very easy to apply, and like very widely used operator. So people use it a lot. Okay, so well, again, so Arnoldi is widely used, pretty classical algorithm. Yes, it's used because it's simple, it's workable. Yes, it's nice because we don't need to find a joint operator of A, which is computationally usually can be a big problem, unless our operator is self-adjoint. Well, and in this research, we showed formally that if you combine it with Tikhonov regularization, our solution, our approximate solution, is guaranteed to converge to original. So although people use it a lot, I didn't see before any research when showed convergence in case if A is infinitely dimensional operator. We control it by, so just making this H the last element, element HM plus first M of Hessenberg matrix. So we stop our process when not the process when this element is smaller than our given epsilon. Then this guarantee to make this difference norm of the difference of this operator, our original operator, and surrogate or reduced operator, finitely dimensional operator A epsilon, yes, smaller than given epsilon. We can apply a truncated TSVD or Tikhonov on the reduced system. Well, for Tikhonov, we select the given regularized parameter lambda from discrepancy principle. Well, and for fixed lambda, the Tikhonov solution for A and A epsilon, they differ by all epsilon value. So that guarantees the convergence of solutions to a solution to the real least square solution X dagger when the noise converges to 0. Yeah, so which makes like definitions of problem is so we say that the regularization converges if when the noise approach to 0, then this surrogate solution approaches to the real solution. Well, that's it for today. Thank you for your attention.